Okay, this is going to be my video about fun with trees max sum. I've gone through everyone else's videos if you turn them in this week, and they were a lot better than the previous week. You went into a lot more detail. Many of you talked about how your algorithm will run on specific data structures like this tree right here. It's a really nice job, but I'm going to try to solve this kind of from the ground up, and I think everyone will learn something from this. Just keep in mind that, of course, this isn't about understanding just the final solution, but rather understanding a kind of thought process that can get you to the final solution, ideally without you having to look it up. That's always my goal, right? For myself is, can I learn something like, let's say, trees and recursion well enough that I can write it on my own? And that's my goal for you as well. So I'm trying to showcase my process here in hopes that you can add some things to your problem solving toolkit. Now, one thing I was kind of surprised about is I put these questions you might find valuable to answer during your learning process. And very few of you actually, very few of you did these. I didn't take off points for it, but I'll just point out that the reason I put these down here is that these are the questions I would ask myself. What's the simplest program that will print out all the numbers in a tree? In what order do they print out? How do I change the order that they print out? So I'm going to do that right now. That's one of the first things that I would do. So rather than trying to find the max sum of a particular path in a tree, which is actually a very tricky problem, I'm going to start by doing something much simpler just to get my head around what a tree node is. Let me think if there's anything else I want to say right before we start. Oh, yeah. So we're going to see recursion in this algorithm. And you've all written a recursive algorithm. Everyone did. So you all know that a recursive algorithm is one that calls itself, a function or a method that calls itself. But really, the notion of recursion is a little bit more general, and we actually can see it over here, too. This is a class tree node that, look, has a variable of type tree node inside of it. So recursion is really anything that's self-referential. Here, this class refers to itself. And over here, in a moment, we'll see a method that refers to itself. It's a weird idea, because we've probably learned, like, in English class, you shouldn't define a word in terms of itself. Like if you defined the word cat as being a cat-like animal, there's something wrong with that, because if you define cat using the word cat, then whoever's reading your definition doesn't learn anything from it because they already didn't know what a cat was, so it doesn't really help to say that it's a cat-like animal. But in computer science, we do it. We're allowed to define a tree node as containing two tree nodes. And we're allowed to define max sum as a method that sometimes calls max sum. So if you think that is weird, then you're right. It is weird. So let's dive into the weirdness. First thing I would do is system.out.println root. That's what I would try first, just to see what happens. I think it's going to give me gobbledygook because I'm printing out an object. Oh, no, it actually gives me... Actually, what this tells me is that whoever created the tree node class actually already built into it the algorithm for printing it out in a nice way. But that's actually not super useful to me, because I want to use the idea of printing out all the numbers in a tree to help me bootstrap up my recursive algorithm. So I'm going to pretend that that doesn't print out in a nice way. What if we wanted to print out all the numbers in a tree ourselves without just feeding it into println? Well, if we look at this little snippet of the tree node class, we can see that there's a value, a left, and a right. So at the very least, I would want to print out the value. Let's try that. Yep. Okay, so now we see 5. 5 gets printed out. And this is our very first opportunity to try some recursion. So we print out the value, and now we would like to print out the value on the left and the right of this tree called root. So let's try max sum of root.left and max sum of root.right. And yeah, we're starting to get it. Starting to get more things printing out. So we see now 5 gets printed out here. Let's actually label that. Let's say value, so it's easier to see. And then maybe here we can say system.out.print left and right. Just to make this printout a little bit clearer. Yeah, so 5 prints out, and then on the left, right before this recursive call, we pass in root.left. This is the recursion, and so that's why we see the very next thing we see is value 4. It looks like we jumped up to this line right here. So it said left and then value, left and then value. Looks like the program ran backwards, but really we just called max sum, and so it's started over right here in kind of a side calculation. So every time the computer makes a recursive call, it stores everything it was doing on what's called the stack. Stores everything it was doing. And then you can think of it as it creates another space in memory to hold everything for the next recursive call. So it starts going through again, prints out value. And then something goes wrong because it says cannot read field value because parameter is null. And so we run into our first problem, which is that if tree node is null, then we can't say dot value or dot left or dot right on it. It doesn't have a value left or right. It's not even really a tree node. It's just the value null. So this is where, and all of you did this as like the very first thing in your algorithm, but it's not necessarily the first thing I wrote, right? I first tried to just do the recursion without this. That's not wrong. You just run into an error and you have to fix it. So you have to say if root equals null, then we decide what to do. At the very least, we want to return and get out of this because we don't want it to continue going in and trying to call dot value on something that's null. But let's also system.out.println, let's just say null. Because I want these print lines to kind of tell the story of how this algorithm is processing its data. So let's see if that helps out. Yeah, so now we get a lot more because we're not running into this error. Let's see if we can read it. So it says value 5. Let's actually find the input. I might be this one. No, not that one. Not that one. Wait, maybe it's this one. It'd be nice if I could get this all on one screen. It doesn't look like that's gonna happen though. It's 5, 4, then negative 80. Yeah, it's this one, right? So 5 prints out, and then it prints left and does the recursive call on the left, which is why we now see 4 being printed out. So left and then value 4. So now it's done 2 recursive calls, And then it's going to, right after that, do another recursive call. So we see it say left again, and then value -80. So if you're imagining the stack of these max sum functions running, we now have 3 things on the stack. So it prints out -80 because it's down here. And now something different should happen because there's no left and no right. Or rather, there is a null left and a null right. So now, on our 4th recursive call, it does max sum of root.left of this -80, which is null. So on this 4th recursive call, it triggers this if statement finally. Prints out null, and then returns. And so then we see left null. Now remember, you have to imagine this stack, because now the thing on the very top of the stack, the recursive call that printed out null, it's gone. It pops off, it's finished, because it got to a return. The one right underneath, that one that returned, is going to continue from here. So that was the -80. The -80 printed out. It printed the left, and it returned, or it printed out null, and now it will continue, and it will print out right. Prints out right, and then does another recursive call. So something goes on the stack again. And then that max sum program runs. Root is null, prints out null, returns, so then that pops off of the stack. So everything I have highlighted over here is the program that runs when -80 is passed in, and the 2 recursive calls for each of the null children of 80. Now, gets hard to wrap your head around. Now that one is done, pops off that stack, or it pops off that from the top of the stack, and now -80 is done being processed because it gets to a return. So that pops off the stack. If I'm not mistaken, there's 3 things on the stack at that point. So after that has run, it pops back up to processing 4, which was never finished. 4 was in the middle of being processed. It was in the middle of this recursive call, which is now finished. So it continues, and it prints out right there. And then it gets to the recursive call for the tree node for number 4's right path. And we see that it's printing out -60. And that gets processed much like 80 because it doesn't have 2 children. So it will do a recursive call on the left, but it returns pretty early with the null. It does the recursive call on the right, also returns fairly early because of the null. And now the 60 is done being processed, and that pops off the stack, and the 4 is also done being processed. It gets to a return. So as you can see, it gets kind of hard to like keep track of how this is all going down. But we are getting everything to print out now. I think I'd like it to print out in a nicer way, personally. Because it would be nice if this printed out in like a tree-like fashion, so it'd be easier to tell like what the structure of the data is. I'm tempted to go down that route because I think it'll illustrate something pretty interesting, or a nice trick when you're dealing with recursive algorithms. Yeah, let's do it. Let's do it. To pave the way, I'm actually going to move everything in here into a new function, because I don't like it being called max sum if what it's actually doing is printing things out. So let's make a new function, a new method here. Call it static. Let's call it static void. There's also no reason for it to return an int. We'll just call it print tree, which will take a tree, node, and a root. Just moving everything I just wrote into a new function. Then I'll call it from here. And I'll make some appropriate changes, like I don't want to return 0 there. And then, very important, if you change the name of the function, you have to change your recursive calls, because this is now no longer recursive. Or rather, it's recursive in a bizarre, weird way, because print tree is going to call max sum, and then max sum will call print tree will call max sum. It is actually still recursive, but not in the way we want. So let me change this to print tree, same as this one. Let's run it again, make sure that it still behaves the same way. It doesn't, because there is some kind of error somewhere. Actually, where is that? Oh, missing return statement. Right, okay, so we still need this one to return 0. Okay, so now it's doing the same thing. And you might ask, why did I bother? Because now it's just doing the exact same thing. The reason I bothered is I'd like to pass in some additional things into print tree. And this is a standard technique when you want to do recursion, but pass along some like context so that you can like build up more information with each recursive call. That might not make a lot of sense yet, but let me try to illustrate it by adding on a new parameter here. I'm going to call it prefix. And when I call print tree, I'm going to say the prefix is an empty string. Hopefully you'll see what I'm doing here. So everywhere I print something, I'm going to print the prefix first. I'll do that actually everywhere. Let's see how that works. Every single place that I print, I'll print a prefix. Now, if I run that now, nothing too interesting happens. I think it's still exactly the same. Actually, we get an error because we added a new parameter to the method, which means that when we call it, we need to pass in an additional value. So if I pass in empty string here, that's where I think nothing particularly interesting happens. The magic's not there yet. Look, it's still just doing the exact same thing as before. But what if I pass in 2 spaces along with the additional, or along with the prefix? I'll let you try to like make sense. Oh, I actually accidentally ran it. Yeah, all right. I accidentally ran it. I meant to ask you to stop and think about it for a second. But let's look at the output along with this and try to think about why that worked. We're seeing kind of a nesting structure now. And it's a nesting structure that matches the structure of the tree. So we see 5 up here with no indentation. And then the left, we see value 4. And then when 4 starts to print out, it's like 60 or negative 80 and negative 60. We see that those are both tabbed in, negative 80, negative 60. And then when those get processed and their null children are printed out, those are tabbed in. Because every time I make a recursive call, I take the existing prefix that came in and I add 2 spaces to it. So that's what I mean by this is a trick to pass along additional information with each recursive call. In this case, I'm using that to kind of showcase a nesting structure. Now, there's various ways we could change this. Like, I could comment out this null, because maybe that kind of clutters things up. And then we would see just the existing numbers being printed out, not the nulls. It was kind of nice. Maybe it would be nice to print line instead of print, just to get things to come out on different lines. That looks a lot tidier. Yeah, actually, I like this one best so far. So now we see 5, and then 5's left is here, 5's right is here. It's kind of nice that we can, our eyeballs can check the printouts here and make sure that it matches the structure over here. So the right side of 5 is all of this stuff, right? Because I just need to line up right with wherever it says value 5. And the right side of 5 prints out value 10. There's nothing on the right of the 10, so we get right colon nothing. And then the left has just a 90, which itself has no children. So we see left, right, empty. So I think this is great. This is actually a really nice function. It's pretty useful because we can use it for debugging. The one thing that's a shame is it already existed, right? Somebody wrote it and put it in the tree node class for us. So really we didn't have to do this in order to print a tree out, but I still think it's a very nice warm-up. Because if you're going to write a complicated recursive algorithm, it's nice to warm up on a simpler recursive algorithm. So this is about as simple as it gets. It's just print statements, recursive calls, and one nice little trick, which is an additional parameter so we can pass data along every time there is a recursive call. Okay, so what's next? So that's the simplest program that will print out all the numbers in the tree. Yeah, what order do they print out, and how can we change the order? So I just want to note that we have a choice here. We could do the recursive call with root.left followed by root.right, but we could also reverse that. So we could recurse on the right and then recurse on the left, and it should totally change the value or the order that things print out. So just take a moment to note 5, 4, -80, -60, 10, -90. Now everything will be different. Let's run it. Yeah, so now we see 5, 10, -90. So the right-hand recursion happens first, followed by the left-hand recursion. Okay, let's try to do something a little bit more complicated than just printing things out. It's the simplest program that will return the sum of all numbers in a tree. Notice I made the print tree void because we don't need to return anything. That all print tree needs to do is print things out. That's its only job. But max sum does need to return a number. So this can be our warm up to that. Let's just call it sum. I'll call it sum tree. And let's system.out.println sum tree of root. And now I'm just going to run this function that does nothing just to make sure that I don't have any syntax errors. So I just wrote the bare minimum, the function that I want, or the method that I want, with a confirmation message in it. And then from the function that's actually getting called, which is maxSum, I'm calling mine. So this one's getting called by the tests. I wanted this one to call my new function, or method. So I call my method there, and then I print something out. This is just boilerplate code to get started on a new method. Yeah, okay, so it says summing the tree. We print out 0 though, so it's not actually summing the tree yet. But let's start. Let's try. Let's think about what would it mean to sum up a tree. And here is where it actually might be nice to have a simpler test. So I'm going to actually try to do that here. So I'm going to copy this test. Let's say custom test, where I am going to delete some of it, just test on the left. So custom test creates a tree node. I just left their code there because I'm assuming that works. And then I'm doing the test on the left one. Let's also put numbers in here that we'll recognize, just so we know that our code is actually running. I'll make them all be 99s. And did it work? It did not work, actually. Oh. It did not work because we need to say @test in front of our method. Let's see if that works. Yeah, here it is, custom test. And now we see our 99s. So this is actually a really valuable trick to remember. It'll work on not just this problem, like any problem you're writing. Sometimes the built-in tests that somebody else wrote for you are too complicated, and you want to test like a much simpler case. In fact, I'm going to make it even simpler. Let's say it's just a leaf with just the number 100, no leaves itself. Like it's just 100. Null on the right, null on the left. Just a single node with no children. Run that. Yep. So here's tree that has just 100. And what's the answer here? Max sum for a tree with just 100 must also be 100. So good to change that because you want this to be a valid test. Otherwise it might fail even though our algorithm is right. And so now we have our custom test. And that should help us figure out what to do in a very simple case. So just imagine that you have a tree that's much simpler than even this example here. This is a complicated tree. Now just imagine none of this exists. It's just a single number, and it's the number 100. So in that very simple case, how would we sum up all the numbers in the tree? It would be something like this. Return root.value. Now, there's no recursion there, so clearly that can't be the end of the story. But that should get the very simple test to work. So let's actually, that actually did work, right? So we see that sum tree root returned 100. And that is, in fact, the sum of a tree that contains only the number 100. So that's looking good. What if let's make a custom test number 2 and make it a little bit more complicated. Custom test number 2. Now we'll do this with leaves. And I want easy numbers to work with, so I'll make both leaves 100 as well. So in that case, the sum of all of those would be 300. Now, remember that we're actually finding max sum here. So if we want this to be a valid test for max sum, the maximum path through that tree is actually 200. Don't have to worry too much about that. I just want to keep these tests being like valid tests for the problem at hand. So I'm going to say 200 there. But what we care about right now for this quick side quest is actually the number 300. So we want to see 300 print out for our custom test number 2. But it's of course not going to, right? So custom test number 2 still prints out 100 because there's something wrong with our sum tree in that we're only returning the root's value. So got to do some recursion here. So here's a try. We could say root value plus sum tree of root.left plus sum tree of root.right. And now our recursion is there. And it kind of makes some sense, right? We say the sum of all the numbers in the tree is whatever number you're looking at, plus the sum of the tree on the left and the sum of the tree on the right. But I have a feeling we're going to run into some problems, and it's going to be very similar to the problem that we ran into before when we tried to print a tree. The moment you put the recursive calls in there, it eventually gets down to where the tree node is null, and then you can't do dot value or dot root or dot left, or yeah, dot left and dot right. So let's just see that happen. Yeah, so we on custom test number 2, we immediately get cannot read field value because parameter is null. So root is null. So now we can start trying to handle those cases where root is null. Let's say if root equals null. Then we return, I would say 0. So you have to think of what is the sum of a tree where the tree has no data in it. I would say 0 is a reasonable value for the sum of a tree that has no data. Most of you in your videos, you wrote this first. You said, okay, let's handle the case where root is null. But you don't have to write that first, even though it comes first in the final solution. You can try your recursion, see that the recursion hits a problem case, and then start adding in if statements to handle those problem cases. Let's see if this actually does handle the problem cases. Yeah. So 300, that's our magic number. That's what we want to see here, because we're summing up all of the numbers in a tree. So that is the value of the current node plus the sum of the tree on the right, or the left, sorry, and the sum of the tree on the right. And if we ever get down to nodes that don't exist, we just say that's 0. And so that ends up being a very simple way to sum up all the numbers in a tree. That's still not quite max sum, but I wrote that down as something to try, because if you're really understanding recursion, then this simpler one should also make some sense to you. So summing up the numbers in a tree. Okay, what's the next level up? What is the simplest program that will return the maximum number in the tree? What about the min? Well, let's just do maximum, because it should be pretty similar to this, I think. So let's see if we can actually just turn this code into max tree. So I'll call this, let's call max tree here. And let's just copy paste sum tree so we don't lose it. We'll turn this one into max tree. Don't forget to change our recursive calls. Max tree. Max tree. And then let's alter our test so that there's an actual correct answer. Let's say there's leaf 101 somewhere in there. Which would actually make this one 201 for if we're trying to find the max path. But don't worry about max path yet. We're just trying to find the maximum number in a tree. This is just still a warm-up sort of like way to get our head around recursive algorithms. So I would like to see the number 101 print out if we've successfully written max tree. Just to remind ourselves, let me write this here. The max number is blank, and let's print out, actually let's just do print tree. So we'll print out the tree and then try to print out the max number. And just for fun, let's do everything. Let's do the sum is sum tree, and the max is this. see how that works out. Okay, so prints out the tree, it tells us the sum correctly, and then it tells us the max incorrectly, which should be expected so far because we just copy pasted sum tree into max tree. So this algorithm is not really finding the max in the tree yet. We need to sort of think about what do we do next? Well, I would say instead of adding these together, what if we found the maximum of all three numbers? Because if you're looking at a tree node, like let's say this one, you're at 17, that's either the max or there's some other max on the left or the right. So you would find the max on the left, you find the max on the right, you compare that with your current number. One of those three numbers is the max of all three, and then that is the max of the tree itself. So I would say we do something like math.max of the root, the max on the left, and the max on the right. I'm not sure if this is actually going to work. I don't know if you can pass three values into max, but that's the idea of what we want, and so that would be the first thing I would try. Let's see. Yep, yeah, it doesn't work. No suitable method found for max int. So sadly, we're going to have to make the code a little bit more messy. Let's do a nested max right here. I'll try to put that onto multiple lines so you can see the structure there. So we first do the max of the max tree recursive call on the left and the max tree recursive call on the right. Find that max, and then do another max between that and the root value. Just a trick to do a three-way max. So let's see if that works. Hey, there it is. Look, max number is 101. Now there is actually a problem here. Let's do custom test number 3. And that problem is negative numbers. So let's do negative 100, negative 101, and negative 100 here. And what should be the answer? Let's actually say negative 99, since that's actually larger than the other two negative numbers. So I would want negative 99 to come up here. Oh man, this is also taxing my brain. What is the answer here for the max path? 199? I don't want to think about max path just yet. Plus it's going to confuse you. Don't think about max path. Let's not worry about this number. Let's just think about, on this tree, negative 100 that has child negative 99 and negative 100. The maximum number in that tree is negative 99. But I don't think this algorithm is going to work on that one, and it has to do with this return 0. So I think there's still a bug. I just want to expose that bug with this new test right here. Custom test number 3, yeah. It says max number is 0. That's totally a lie, because 0 is not a number in this tree. It's negative 100, negative 99 on one side, and negative 100 on the other side. There's no zeros. So this part right here, although return 0 made a lot of sense for if we're summing a tree and we get down to a null node, the sum of a null node probably should be 0. But the max of a null node, I think, should be negative infinity or something like that. So actually, I always forget this. Let's just look it up. Math negative infinity Java. Oh yes, integer dot min value is what we want. Let's do that. Let's try integer min value. And custom test 3, max number is -99. So that's working just fine. So this is 3 side quests we've done so far. Printing out all the numbers in a tree, summing up all the numbers in a tree, and now finding the max number in a tree. You'll probably notice that they have a similar structure to them. Handle the null case, and then do stuff with recursive calls. Handle the null case, do stuff with recursive calls, and handle the null case, and do stuff with recursive calls. So seeing a pattern arise here. I think we might be ready. So if you have a program that returns the max number in a tree, how far away are you from returning the max path in a tree? Let's do it. We're printing out all our side quests, but let's actually do the main thing. We'll call it max path. We'll pass in root. I'll start by copying max tree, which is going to be wrong, but it's just sometimes nice to start with something wrong and make it correct. And yeah, so we're getting the wrong answers, but we are getting numerical answers now because we are returning the maximum number in a tree when in fact we want the max path. So we're returning the right kind of data, it's just the wrong answer. And so the question is, how far away are we? What do we need to change about an algorithm that finds the max path? Whew, I almost made a mistake here. Need to rename these method calls so that it stays a recursive algorithm. But if we take this recursive algorithm for finding a max node in the tree, actually, I kind of want to call this max path tree, because I called this max tree and I called this sum tree, and this one was print tree, so they all end in tree, and so max path tree matches that pattern. So I'm gonna rename it to that, and then change my method calls as well. Oh, and then gotta call it correctly here as well. Okay, all right. So now we're ready to tackle this last part. You have a program that returns the max number in a tree. How far away are you from returning the max path in the tree, the actual Code Wars problem? So would there be a way we can make some tweaks to this max path tree method to get the right answer? Well, let's think about our data. Let's actually think about the simplest of the data. So the simplest test is called custom test, and it's just a single node, number 100. So that would be root.value. So let's keep everything there, but let's start this process over, just thinking about the simplest piece of data on up. So if I say return root.value, I will actually pass custom test number 1, because that is, when there's a single node, its value is the sum of the max path through that tree. Let's do that. Hey, look, 1 test passed. Yes, custom test number 1. This one, whose value is 100 and has nothing on left and right. We're finding the sum, we're finding the max, and we're finding the max path. Okay. But we are failing on this one. So this is the next most complicated input to our method. And it has leaf 100, but then 101 on one side and then 100 on another side. So that 101, that's the max path. So using the same kind of pattern as before, we do know that we're going to need this if root equals null. Let's do that. Let's say if we get down to nothing, then we return integer min value. Does that make sense? Or do we need a 0? Who knows? We'll figure it out when we get there. In this input, we would want to find the max on one side, the max path on one side, and the max path on the other side. And whichever one is larger, when you add on our current value, would be the max path for the full tree. So notice I'm thinking about a very simple tree here. I'm not thinking about my algorithm on this tree yet. I'm just thinking about it on my custom tree with only 3 nodes in it. If I can get it to work on a very simple tree, then I should be able to rely on the recursion to make it work on bigger and bigger trees. So we'll come back to this return, but let's, as many of you have done, this should look pretty familiar. Let's capture the 2 outputs on the left and the right. Max on left is max path tree root.left, and max on the right is max path tree root.right. And then one of those is larger than the other. So we can say int max on left and right. I don't know, maybe that's not the best name. How about global max? So max on left, max on right, and then we calculate global max by saying math.max of those 2 numbers. And then whichever one is the max, whatever global max is, we'd want to return our current value plus that. So even before we run this, we should be able to test in our brains, we should be able to test that on our simple data. So let's test it on the very simplest data first. So leaf 100. We should be able to run this program in our brains on this simple data. So tree node, that's just 100, no children. All right, max path tree gets called on that node. It calls max path tree on the left and then on the right. But we know those are both null, so they're going to immediately return integer min value. So we have max on the left is integer min value. Max on the right is integer min value. Global max is the max of those 2, which is integer min value as well. So we're going to end up returning root.value plus integer min value? Is that right? What happens if we return the min? Actually, that would be a giant negative number, so I feel like this is going to be not correct. So I think we've written an incorrect algorithm here, but let's see if it is incorrect in the way that one would expect. But I have some suspicions about this part. Okay, let's find our custom test number 1. Yep, it's not working. We expected 100, but we got this giant negative number. So my suspicions were correct. All right, let's take another stab. Let's try 0. Because if we had added 0 at this step, it would have been correct. Hey, look, that actually passes several tests now. So maybe 0 is the magic number. So custom test 1, 2, and 3 are all correct. Do we get anything else that is correct? Actually, we get almost everything is correct. Wait, what? Is that right? Max sum in null tree. Oh, all right. I forgot. These are our printouts for our side quests, so we don't need to worry about that one. But we should figure out why stop it only leaves is not working. But let's take a moment to celebrate the fact we actually passed most of our tests here. So our 101 or 100 that has 2 children, 100 and 101. We passed that one. which I think makes sense because when the 100 comes in, it does one level of recursive calls. Actually, two levels of recursive calls. It goes down the left side and finds the 100. Its children are null, so those zero out. It goes down the right and finds the 101. It finds the max of those two, which is 101. And then it adds the current value to 101. So thereby returning the max path in this fairly shallow tree. So that's all looking pretty good. I mean, I think we've taken a good stab at it. So why are we getting the wrong number at should stop at only leaves? So what is the actual, okay, so it's expecting negative 51, but it was 15. So is this a problem? I think it might actually be a problem with return 0. But this is a pretty complicated tree. It would be nice to find a simpler tree that also fails. We do have one with negative numbers, and we have one with positive numbers, but we don't have one with both positive and negative numbers here. So I think that's the problem here. So negative 51 is the right answer. Why did we get 15? So doing 5 plus 10. Oh, yeah. Right, so I think it came up with 15 because it processes 5. It goes down the right, processing 10. And then it goes down the right of that and it gets 0. Because we returned 0 when there's nothing there. And it thinks of that as a valid path. It's like, oh, 0 plus 10 plus 15 is a big number. That's way bigger than what you would get if you go down this other path. And so it calculates 15. So we need to do what many of you did in your algorithms, which is we need to not let it get down to this point where root is null. Because if it's getting down to that point, then we've gone a little bit too far. We don't want to count zeros, or we don't want to count null trees at all. So right here, when we're doing max path tree and we're doing root.left, we've already gone too far. We need to check before we make this recursive call to see if there is even something on the left. So what I'm going to do is I'm going to start by putting a print line here. And I'm going to say alert. We shouldn't get here. We're getting here now, but I want to restructure the code so we don't. So this is the first thing I'm doing, is putting something there to tell me if we ever do get here. Then I'm going to take everything we've written so far, and I'm going to put that into an if statement. Because this is actually perfectly fine to do as long as there is a root.left and a root.right. So I'm going to say if root.left is not null and root.right is not null, then we do this perfectly acceptable algorithm. Now, what are our other cases? So if we get past this one, then let's say we have something on the left, but right must be null. Because if they're both non-null, we get in here, and then we return something. So if we've gotten past that, and root.left is not null, then root.right must be null. Does that make sense? So we had an earlier case to check that they're both non-null, that there's two children there. If there were 2 children, this would have run and we would have returned. So if we got past that, we know there's not 2 children. This next one checks to see if there is a child on the left. There's not 2 children. There is a child on the left. Therefore, if we get in here, there's not one on the right. Because if there was one on the right, it would have gotten handled by this if statement. So this is checking, because this comes after this is checking the case where there's only a child on the left. So imagine some tree where there's only a child on the left, and you should be able to identify the thing that doesn't need to happen, which is max on the right. We don't care about max on the right anymore. And we don't really need to do global max either. We just need to find the max on the left and then add that to root.value. I think. At least that makes sense to me. That's going to be my first stab at this. So now, of course, just by symmetry, we want to check the case where there's only one on the right. And then, obviously, we want to check max on the right. So I'll rename that variable. I'll say this. And then if both are null, we actually don't need an if statement for that. Because we've checked the case where there are 2 children. We've checked the case where there's 1 child on the left. We've checked the case where there's 1 child on the right. If we've gotten past all of those if statements and returns, we're now at the case where there are no children. If there are no children, I want to just return root.value. Because we're back in that simplest possible case, custom test number 1, where there's just a value, no children. If there's just a value, no children, then that value is the max path. So this handles that simplest possible case. These two handle the cases of 2 or 1 child. And if we get all of those correctly handled, I think we should never end up in this case. But we'll see. We'll see. So we'll run that. All right, we got a typo somewhere. I think I said max on left here instead of changing that to max on right. Oh, there it is. Yeah. Yeah, and we don't see this printout, which means this is actually dead code. It used to be alive, but now it's not. We made sure we can never recursively call that far down. Let me just comment that out because maybe I went kind of fast earlier through that explanation. You might want to pause the video now and try to think about why is it the case that because of the changes we made down here, I'll make this bigger. I'll move myself out of the way. Because of the changes we made down here, we can actually never get into a case where we call max path tree with a null input. This will never be null. And it's because we're doing a lot of left-right null checking beforehand. So we first check, is there something valid on the left and the right? If there is something valid on the left and the right, then we can do both recursive calls on the left and the right. So we're never calling, in this if statement, we're never calling max path tree with anything null on the left or null on the right because we check both are non-null. All right. Now we get past that. We check to see if the left is non-null. And if so, it's totally fine to do a max path tree on the left. But we omit the max path tree on the right because we know that one's null and we know there's not a path there, so we don't make the recursive call. And then we do the same thing on the right. If it is non-null, then we do the recursive call on the right and not on the left. We omit that one because there's no path going to the left. There's no child there, so we don't do the recursive call. And because of all that checking, we never end up calling this with null, So this is no longer necessary. We never need to check, hey, did we get called with null? It just doesn't happen. And so then that passes all of our tests. Now, will it pass all of the tests if I press attempt? Maybe not. Oh, actually, did I just... max sum... yeah, okay. Max sum in null tree. Max sum in a null tree is the one edge case, which is what if it was null to begin with? So they pass in null here at the very top. They just give us a null, no tree at all. Then we call max path tree for the first time with null. Then there is a problem. So we could either put back our check right here, or since we know we're not ever calling max path tree with null, as long as it was not null to begin with, we could check earlier. Just before we make our very first call to max path tree, we could check to see if root is null up here. Either one will work. So let's run that. Yeah, and that passes all of these. Let's press attempt, see if it works on the hidden tests. And it does. Yeah. So then that's my path to solving this problem. So just to review here, first side quest is could I print out the trees using recursion? Which I did. Could I find the sum of all the numbers in a tree using recursion? Which I did. These are not too bad. These are not too bad because we can make this assumption that once we get down to null, there's a reasonable value to return. Same with max tree, same thing. Once we get down to null, after recursing all the way down to the bottom of a tree and falling off the edge of the tree at the bottom, there's still a reasonable value to return for null, which is just integer min value, because that makes sense in the context of finding the max. But then things got complicated, right? And I think you can sort of see that the complexity came because of what we're allowed to do once we get to the bottom of a tree. Like what's at the base of that tree, or the base case of our recursion. That's what makes things kind of complicated here. And many of you had different solutions where you're handling those base cases in different ways, but you're going to have to handle them some way or another. And so what happened here was, at least to me, a little bit frustrating because we were very close without having to have all of these extra checks, but still wasn't quite right because we were still returning 0 at the null case. And that makes it feel like to the algorithm that going off the edge is a valid path, but in this problem, it's not a valid path. You have to, you can only stop at valid nodes. And since you can have negative numbers, 0 is not a good number to return when you go off the edge. So we had to make sure we never go off the edge as we're doing the recursion. And so hence all of these protections get added. But I tried to solve this in an authentic way, and I really just want to point out, because very few of you did this in your problems or in your solutions. I didn't write all of these to start with. I very much wanted this to be a simpler solution. Because look, sum tree and max tree are so simple. It would be nice if max path tree were also that simple. So I tried the simple solution first. And then only when it failed did I realize, oh, it needs to be more complicated. And so then I added some complexity. So yes, my final solution has some complexity to it. But I got to that complexity by adding only things as I needed them. And that, even though no one ever knows that once they read your final code, that is the authentic practice of writing code, is that you'll end up at whatever level of complexity you need as you solve problems here and there, handle more and more corner cases, and then ultimately arrive at your final solution. So hopefully this was a good, just, 2-week tour of recursion, which is perhaps one of the most interesting concepts in programming. It's anytime something refers to itself. And good rule of thumb is if you have a class that refers to itself, then all of the interesting things you do with that class are going to be methods that refer to themselves. So it's not a coincidence that we have all of these recursive methods to process a recursive data structure. That's to be expected. All right. I enjoyed your videos. I hope that you learned something from this one. And I'll be posting your next week's homework very shortly.